Okay, before we go into the tracking part, so we are going to. I just want to. I missed the swap part, so I will just quickly mention what is track swaps. So, like we talked about broken tracks, right? So you know that in the broken tracks, whenever we see a number 0 from a number, then we count as a broken. So the swap, what we do is basically it says like this, right? So one track is going this way. Say, let's say for example this. So certain point the black is associated. After that blue is associated. Then we say that associated track is swapped. Okay. So in order to do that, what we do is every time we do the association. Okay. The association at up to this point, associated ID is 1, then the associated ID is 2. Then we say that there's a swap. Okay. Now, because of that, now what we do is, so whenever you see a change in number, we in this case we don't say swap. Whenever we 0, we don't say swap. That's not how we define 0. Swap, right? Swap is calculated at only at this point. Only at this point you see a swap. Up to this point, track 1 is associated. After this point 2 is associated. That is when we define a swap. 0 we don't worry about. Okay. And the second part, if you look at this is one swap. This is another swap. Whenever a number changes, like 1 to 2, one swap, 2 to 3, another swap. That's how we define the swap. Correct? Okay. Now we are going to move into the real tracking. So at least I prepared a slide to our lecture to show how to do a simple track. Okay, so if you know this, I believe you can implement a simple tracking. That's it. Okay. Now, before we start, let me think about the actual code that you write. So usually, if you have a Monte Carlo runs, you will have a for loop here, 1 to say 100. Inside this, you will have a for loop for time step, say 1 to 50. Are you okay with that? That is the end, and that's the end. That's the normal tracking. Then what you do is you get the measurement that generate or get measurement from data. Are you okay with that? So we are going to generate measurement. If it's simulated, if it's a real problem, you get the measurement from a CSV file or network, whatever it is, you get the data. Once you get the measurement, then we are going to do the tracking. Okay. In the tracking, we have a few things. One is track initialization. Data association. Filtering. Then track management. So these are the main things that we are going to do. So filtering you already know. Okay. So filtering I'm not going to talk too much about that. Filtering is a nonlinear filter, Karma filter, whatever it is. But we are going to have track initialization, data association, track management. At this point, I believe you understand each module, right? So can someone explain what we mean by track initialization? That means how to initialize a track, right? Because we are going to have tracks. tracks are going like this, how to initialize the track. And the other one is the data association. Once you have a track, you get lots of measurement. You want to associate a track, measurement to the track. Once you do the association, do the filtering. Filtering as well. And eventually, we will do the track management in which we change the statuses. Confirm, tentative, dead. So these are the main things that we want to do. Okay. So now I want to bring this inside the code. Which one is the first one? Initialization. If you are saying this comes first, one, then two, then association, three, and then four. Right? That's what you think, right? But ideally, this is the first one. And you can say this is the second one. Third one, either one. Okay. Usually you can have this third one, or you can have this as a third one, and this as the last one. Okay. You thought that track initialization will be the first one to do, but usually I would do the track initialization at the end. Okay. The reason is that, because like in the slide, that's how I have. But anyway, I am going to teach first track initialization, right? Then others, but track initialization is usually the last part. Okay, now we are going to talk about track initialization, and we will talk one by one.
What is the first loop?
One is the Monte Carlo. That is only for simulated data, not for real data. The for loop is the other one is the internal for loop. Okay, now we are going to focus on track initialization. Once we mention what is track initialization, then you understand why we do here, not on the top. Okay. So at time k equal to 1. Are you okay with that? So we don't have any tracks at that point. That's empty. That's okay. Now you have for detection. Then what do you do? There's no association because no track. So what do? You create 4 new tracks. Is that clear?
These detections may correspond to single target.
Yeah. So in the whole course, at least for now, we assume only one measurement comes from one target, right? 1 to 1. So that means like we don't know which. Extended targets are a different problem. Self-driving car having multiple detection is a different problem. So in this course, to simplify everything, we always assume a target is a point target. One measurement comes from one target. So that means one measurement can create a one new target. Okay. So this is what you would do. Let's say now you go at k equal to 10. You already have 4 tracks. Okay. Now you get that 5 detection. What do? You understand that? Earlier I said, is it possible to close this button somewhere? Okay. So at k equal to 1, so we have 4 detection, we create 4 new tracks. Okay. Now at k equal to 10, I already have 4 tracks. I have 5 detection. What do? First, we do the data association. You can't say that I will create 5 new tracks. You can't say that. That is why we don't do that as a first step. You are not going to create 5 new tracks with this. What you are going to do is, so you do the association between track and detection and say that 3 detections goes with the tracks. Are you okay with that? So only 2 unassociated track measurements. So you understand? This is the important part. So you find the measurements that are not associated to any of the track. that clear? Then how many new tracks that we are going to create? Only 2. Correct? So what we do here is that I will talk about the data association next. But before that, what you do is, so you have 3 tracks here, here and here, and their covariance are like that. And say you have detections here, detection here, and say detection here and here. Okay. So in this case, with the data association, I say this goes with that, this goes with that. Then I will create a new track with this, new, and new. Clear? So I find the measurements that are unassociated with the track, then create a new measurement from that. Okay, if you understand, then now if we go back here, you understand why I put that as the last one. Right? Is that clear? Because we want to see whether these measurement comes from this target, then update those tracks with those measurements. With the remaining measurement, we will create a new track. Okay, that is how the initialization. So if I see that unassociated measurement, that measurements are not going with any of the targets are used to initialize new tracks. So next, what now we are going to talk about initializing a track. So I said that one track, say we are going to initialize a track, say level. Say I think we already have 10 tracks. I'm going to create a new track. So we want to give ID, X, T, and state. Okay. So this one we always say is tentative. When you create a new one, you say tentative. And this one, what can be the ID? The last ID plus 1. Yeah, or you can say level. Now, mainly we are going to talk about how to do these two. That is the main thing about track initialization. Okay. So now let's start with the X itself. X should be X, Y, so X dot, Y dot. These are the 4 things that we need to initialize. Using, let's say radar, right? Radar has R and theta measurement. Then we convert that into X converted and Y converted. And corresponding R converted 1, R converted 1, 2, R converted 2, 1, R converted 2. Are you okay with that? I think we already talked about that, right? So you have R theta measurement, each measurement you convert and find the corresponding coordinate. So clear? Now we are going to initialize that. So how do you initialize this? X. Okay, can you start with X? What can we do for that? This one, right? So that's the best thing then. So instead of X, you will see XC. I will come to this part later. Y becomes YC. And then, are you okay with that? Right. So I use a measurement to do. And this initialization, whatever I talk is for a fully observable sensor. Angle only sensor, I can't use whatever I say. Okay. Assume the sensor can be converted to the X and Y. So I do this. Okay. Now, what can we use here? You assume V max is not. The V max is 100 meter per second. So that depends on the scenario, right? So if the scenario is tracking some target, so you know that maximum speed is 100, right? So how do we initialize the states? Should I put 0 here or should I put 50? Which one is better? Because I don't have any other information, so I'm going to use my prior initialize a state. What do I put? 0 or 50? What do you like? 50. Any other answer? Because we don't know anything on the speed. So we want to give some value for speed, right? We want to give a value for speed. But let's, like when we initialize a target, mainly we have to talk about X and P. For P, what do you give? What is this corner value? That is going to be R11C. Correct? That's a coordinate that we get from the mesh converter. When we copy that. Then where will this go? The 2 will go here. Are you okay with that? Then this one goes to this part. Okay? So then it comes to here. Okay? So clear? Now about the velocity, we don't have any information. Only thing that I know is that B max. So what I would do is I will initialize that as B max divided by 2 all things squared. 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, and B max divided by 2 all things squared. Okay, so basically what we say here is that if you have a uniform distribution between these two, right? So you don't know anything about it. You will find the mean value, and the standard deviation is usually d over square root of 12 for uniform distribution. But usually instead of using square root of 12, usually people use B max by 2 and holding that. Okay, that's how we initialize the covariance. That's this part clear? I believe you are clear with that. This one we give to capture the error in the velocity because we don't know anything about the velocity. Pardon?
R2.
R. This one? Yeah. R will be around Y, right? Yeah. Okay. What is your question?
Is that around Y?
Yeah. So here, if you look at this, this is X. This is X and this is Y. Right?
So R2 is the covariance of Y direction.
This is the corresponding covariance. This is the corresponding covariance. This is the cross covariance. Right? So this is the covariance in the X direction. This is the covariance in the Y direction. This is the cross covariance. Right? So that is why it comes with it. And then for velocity, we don't know anything. We can't. Okay? Now go back to this. If you understand this part, so this is uniform distribution. We pick the mean as our known estimate and standard deviation. So what should we use here? 0 or 50? The reason is that we will go with 0, not 50. Okay, so we don't initialize with 50, we initialize with 0. What is the reason for that? I said uniform distribution, I will pick the mean. So what is the mean? Is it 0 or 50? Okay, let's see. If the V max is 50, what are the possible values of V? We can take minus 50 to 50. Are you okay with that? Right? It can be on the negative side as well, or positive side. So it's a vector, right? So it can be negative to 50. So what is the mean now? 0, right? That is why we go with 0, not 50 or 25. Sorry, not so in our case 100, right? That case we say 100. So this is 100. This is 100. The mean is 0. Right? So that is why we initialize that to 0, 0. That's it. This is the track initialization. I will talk about another approach called 2-point initialization. But in my trackers, even though it's used in real system, I always use this. I don't use 2-point. It may have some slight advantage, but this is the easiest and best ways to do. Okay, so if you are going to implement something, I would say as long as you know this part, you're done. Okay, so you go with 0, 0, and there's that. Okay. Now let's get right to make it complicated. I don't have anything on the slide. So you want to track the vehicles going on this road and assume this is a one-way road. Not in Patna. I think Patna, I have seen that if it's a one-way road, I think they go in the other direction as well. I don't know, it's allowed, right? But it's not that kind of road, but say you can go only in this case. In this case, how would you initialize the state? So I have X and Y. And for the velocity, what would you use in this case? I think this is X axis and this is Y axis. What would you use for velocity here? Is it 0 or would you use something else? What that something else might be? In this case, it could be 50, right? Because the range is not minus 100 to 100, it could be 0 to 100. Right? But if the road is slightly slanted like this, maybe a different range. Right? So basically, you map your prior into the initial state. That's all. You understand the initial the prior that you have and do a proper mapping. That's all we do. Okay, but okay, that's one. Now I said that sometimes we use Vmax by 2. About the covariance, right? So in our tracker, that is the main problem I have right now. That sometimes, like what happened is that I use Vmax by 2, all things squared. Okay, so that is what I have. So I always have a tracker parameters and do it. So then in the parameter file, I have a Vmax. That is say 100. Then accidentally, not accidentally, actual another scenario, actual target speed is say 200 meter per second. Actual target is moving with 200 meter per second. My prior, I use Vmax is 100. Okay, I initialize the covariance like this. What is the consequence of this? What do you think about that? Admit? Admit or deny? Okay. What is the consequence of using a similar value compared to the actual value? Because sometimes we spend days, okay? It's not joke. I spend days to find out a problem. So sometimes we get a new data, we run the tracker and it's break and so on. We spend days to debug that problem. Then eventually found out, oh, I forgot to change the Vmax value. Simply it's like that. Okay. So what is the consequence of using a smaller value here? Confirmation will take time. Okay. Why? There are two things. One is filtering problem. Other one is the tracking issue. Filtering perspective. So your coordinates is not consistent and you give a different weights for the prior and the measurement. So it may take longer time to convert to the actual value. Okay, that's one issue. But the major problem comes in the data association. Sometimes you may not get any confirmed track at all. Okay, if you use a wrong Vmax, that's what we see. No track will be shown. then we go to the code and put a breakpoint and debug and so on. It's not easy to identify the problem as well. But if you use 100 here instead of 200, what might happen is that the next topic's data association, right? So that anyway, I just want to connect all of them so that you guys understand that. As a first thing, what we do is I initialize a track. So we have a Vmax, the covariance of velocity. So next time, this is K10. K11, you want to do this. The Kalman filter, you want to do this, right? The prediction. Right? Where is the predicted location of the target at K equal 11? As if we just initialize the track, then I want to go to the next step and process the measurement. Where is the predicted track? Pardon? Okay, inside that circle? Oh, inside the circle where? You understand the question? This is the position at time K equal 10. So now K equal 11, I want to do the predictions. Where is going to be that? Where is the predicted state? Okay. So, okay. If you see this is 0, that is 0. It's going to be the same. It will not move. Okay. So it's going to be the same location. How about the covariance corresponding to that? It's smaller than blue circle or greater than blue circle. So that is going to be like that. Okay. This distance depend on your Vmax by the 2 holding square. If that Vmax is larger, then it goes little larger. Is that right? So since your velocity covariance is small, you think that 0 and that is 0, that means you have the blue one. But if the actual measurement somewhere here, you say that that measurement cannot come from this target. Because that's outside my region, right? First of all, whenever I plot this, I believe you understand this part. That is the ellipse, right? So what we plot here is the, because like from now onwards, I will always work with that ellipsoid, right? I believe you understand the ellipsoid of that, right? Say, if you have a mean here, and this is usually 19, say, you say 99% confident region. So with the Gaussian distribution, the single dimension, this region, right? Basically, this is a region where the measurements can fall in. But if it's 2 dimension, then this is an ellipsoid. Covariance can be mapped to this ellipsoid, right? So this is 99 confident region. That means the actual target is inside this region with a 99 probability. 1% it could be outside. Okay. So now if the measurement is outside of this, we say that that is not the measurement from this target. So we call this as a gate or confident region. Okay. So now we say that this cannot be from this. So we don't associate the target. So that is a problem with this. If you don't set the proper covariance for the velocity or anything, your covariance could be smaller than the actual one. The measurement can fall here. Then you will not associate. What happens if you don't associate? Then you create a new track here. New track here. You keep on creating new tracks. None of them is confirmed. Right? So you won't have any actual target at that point. So this is a simple mistake that you made, but the consequence is that you won't see any tracks at all because of that. Is that okay? So that way the covariance should capture the possible error that you can have. Okay. Okay, so with that, I believe 30 minutes. Okay. With that, I believe you understand initialization. That's the main thing about initialization. I can now quickly go through the initialization and then talk about the other thing later. We say that it should be consistent. And when I say consistent, the covariance should be consistent, right? The covariance should be satisfy the uncertainty. Must reflect the activity and so on. So far we talk about 1 point initialization. The another approach called 2 point. The idea of 2 point is to initialize the velocity as well. Okay. So in the 2 point initialization, what we do is the 2 point initialization, I will quickly summarize that, but we don't want to spend too much time here because it's a little complicated. In the 2 point initialization, what we do is this is k equal to 10, k equal to 11. Instead of initializing the track at this time, you wait one more time step and initialize here. Okay. So what you do is you initialize the state here with x converted at 11, y converted at 11. Instead of putting 0 velocity, we are going to have x 11c minus x 10c divided by time. Clear? You have two directions here and there. So you estimate the velocity from it. Right? That's the basic idea. Similarly, you find the velocity part also similar to that. That's the idea of 2 point initialization. Use 2 points to estimate the velocity as well. Yeah. Main thing that you notice that in one point, we initialize the track at k equal to 10. First update, Kalman filter update happens at 11. You don't update again at 10. That is wrong. You don't update again. In the 2 point initialization, you initialize the track at k equal to 11. Kalman filter update at 12. Okay. So you don't reuse this information to update the filter again. Some people make that mistake. Don't do that. So use the K10 and 11 to initialize the track at 11. Then you use the Kalman filter update from 12. Is that clear? So that is the 2 point initialization. But I again repeat that unless you want to write a new paper on 2 point initialization or initialization, I would say you go with a 1 point initialization. That's it. Okay. I would recommend just take the 1 point when you don't need to read more about 2 point. Right. Okay. So if I quickly summarize, that's what we do. Right. So in this one, you can consider 11. So we get the position and the velocity. We subtract the previous one divided by t. That gives the velocity. This is 1 and 0 or 10 and 11. We are away now. Okay. Then you find the corresponding covariance for the velocity. The velocity covariance is covariance of this plus covariance of this divided by that. So that is why you get it. Okay. So if you know about the variable, the random number, this is a random number, this is a random number, covariance of this is R, covariance of this is R. So covariance of this is going to be that. Okay. That's that. Okay, this is the last point. If you use a constant acceleration model, not a constant velocity model, if you use a constant acceleration model, then what do you need? You need to have x dot, x double dot. In order to initialize this, you may need 3 points instead of 2 points. Okay, that's what it says. Okay, but in practice, we don't do that. Okay, so if I finalize that single point initialization, we set these to the converted values and 0 here. And if we use a turn rate model, again we set that to 0. Okay, and then you see that we already talked about 1, 1 and that, and then I said we max by 2 volume square, that, and if you have a turn rate, then omega max by 2 volume square as well. That's clear? Okay. This is a simple comparison of two single point versus 2 point initialization. After a few frames, both of them will give the same answer. Okay. First 2, 3 frames, this may be slight different. After a few frames, you will get the same answer, right? So that's why it's not that much different. But the single point initialization is Bayesian approach because you use a prior and update use a Gaussian. This 2 point is based on the maximum likelihood estimate using 2 frames, but eventually it comes to the and the Poisson approach 0, then both of them are equivalent. Okay, so that. Okay, I'm going to skip this because of the time limitation, and we were talking about how to use Doppler, right? So Doppler means range state. We talked about range state in the last class yesterday. If you have range state, that has some information about the velocity, right? But usually, I don't say whatever I'm doing is correct, right? But sometimes I take a lazy day, maybe. Usually, I don't use a Doppler to initialize the measurement tracks. I use the Doppler to update tracks. Initialization, I just use 0, 0. I don't use the Doppler information at that point. But from now onwards, I use that to update the track. Update, then need to catch the velocity sooner, right? That's one thing. But if you want to do initialization also with Doppler, then you have to follow this equation, right? So you will, this is the Doppler equation, then you will initialize the initial velocity using a mean square estimator. It's a little complicated, okay, but still, that has information. That's what I say. Doppler measurement has some information about the velocity. Without Doppler, we always set to 0, 0 because you don't have any other information. The range state, if the radar can measure the range state measurement, you get some information about the speed, then that can be converted to the initial state. Okay, I'm not talking too much about that, how to do it, but we can. This is the other thing that people are asking about, how to initialize with the passive sensor, angle only sensor. Again, this is a harder topic. So in this one, we are talking about, say, you have 3 passive sensors. 3 angle only sensor, you want to initialize the state. So I see no clutter for now. Right? So where is the actual target? So maybe you would initialize somewhere here. Are you okay with that? With this angle, say somewhere here. That one says somewhere here. This one says somewhere here. And if you do this triangulation, eventually it will somewhere here. But here, what we assume is that data acquisition is already done. Right? So we assume that because data association itself is not a problem. Once you do the data association, if you know that these 3 measurements are coming from a target, then you initialize the target at this point. Graphically, that's what happens. But mathematically, what we do is first you pick this point, one of the intersection, then you would use an iterative least square approach to convert this into this point. Okay, so because it is only 3 measurements, it is 4 measurements, 5 measurements. So what you do is you start with an initial guess, then you iteratively you improve this position, and using that iterative least square estimator equation, eventually you will come to this as the estimate. Okay, so that is how you do with the passive sensor. But one question was how we do the data association. That is little more than that. But you need to do this even in the data association. But you would do. I'm not going to talk about that, but because I don't have time, but I'll quickly mention that. have a sensor 1, sensor 2, sensor 3. So you have measurements like these. Okay, these are the angle only measurement that you get. Now what you do is you consider all the possible pairs that you can have. Okay, for all these pairs, you want to find likelihood. What is the likelihood of having these three pairs? So similarly, you will find the likelihood of all the pairs using this triangulation. For a given association, you can find this and see how likely that tree comes from the target. So once you find likelihood, you formulate this as an assignment problem, SD assignment problem. You can read any paper on that SD assignment problem, or again any specific paper on angle only association. So basically, they formulate this as an assignment problem. They find the likelihood for each assignment, then solve it. That is the optimal assignment for the angle. Okay. So in this case, the velocity estimate is similar to the one for initialization 0, 0. And the covariance, usually we use CR because we don't have any way to estimate the covariance. We estimate the CR using those three measurements. Then we use that as a code. Okay. Okay, we are done with initialization. Now I am going to move to the next part of the tracking. That is the data association. I don't know how many of you know about the trackers. So there are several trackers. Nearest neighbor tracker, MHD tracker, PDA tracker, JPDA tracker, MFA tracker. All these names of these trackers come based on how we do the data association. Okay, the data association is the one deciding the name of the tracker, not the initialization or filtering approach. Mostly, the trackers are named by the data association. That way, you see that there are several ways to do the data association. So in this course, at least I am going to talk about simplest way to do data association. That is called nearest neighbor or global nearest neighbor. Okay, that is the approach that we are going to study. Okay. So because of time limitation, again, I'm going to skip this one to talk about general data association issues. So I will skip this. Mainly, I will jump into the data association part. When we do the data association, this is our assumption. 1 to 1. One target generate only one measurement can generate only from one target. Okay, that is the basic assumption we have. We can miss a target or the measurement come from a clutter as well. Okay, for an example, say we have one target and one measurement. How many possible associations that we can form with them? Okay. So there's a one target, one measurement. You want to consider all possible associations. How many possible associations that we can have? Okay, let's talk about that. What are those? First is like say this is 1 and 1. I say 1 to 1. That is first assessment, right? What is the other one? Second one says that is 0. No measurement, but this is a and a false alarm. Right? So that's a simple example of it, right? Even if we have 1 and 1, we can say, okay, this comes from there. We know this is missed and that's a false alarm. Similarly, you can have multiple hypotheses. We call this as hypothesis. You can have multiple different hypotheses to form with them. Okay, now let's talk about the real one aspect. I'd like if you understand one, then you can understand. In any tracker, most of the tracker, like I would say, like at least the trackers I meant so far, gating is the first step of tracking. Okay, any tracker you have a gate. Gate means gate graphically, like let's think graphically. Then you go to the method. Don't worry about the method at this point. Are you okay with this? This is the predicted state. This is the confident region. Are you okay with that? Now we convert that. Now we are talking about common filter. That's why I spent a little time yesterday. So we convert this into this point. That is at k into k minus 1. Is that right? And then this is the S. Do you remember what is S in Kalman filter? Innovative covariance. The covariance of the measurement, right? So this is the S of the covariance. Okay. And the size of that, okay, size of that could be this or this. This is a gauge size 1. This is gauge size 2. Say this is 0.99 probability and say this is 0.95 probability. You understand that part? If you want to, that's a gauge size. So when we say gauge size, I want to consider 95 confident region. That means 95% that is going to be this smaller ellipsoid. If you think a 99, it's going to be in this bigger ellipsoid. That is the gauge size. Okay, so when we do the gating, first we define the gauge size. That is basically this probability. So first you define, in order to define the gauge size, even in the assignment, I think I can show that. First you define the probability, say 0.99. Then you will find the measurement size, that is 2. Because r and theta, so the dimension of the measurement is 2. Then you would use MATLAB psi 2 inverse with this 0.99 and 2. That would give something like, for example, 9. That is the gauge size. Okay, that is the gauge size that you are going to use. So that will define how far you can go in that. You understand the gauge? So now if you come here, if a measurement is somewhere outside, I say that the measurement is outside the gate. If it is inside there, then we say inside the gate. Okay, so that is the idea of gate. So what we do is, so you get usually in the normal radar, so if you are working with the real radars, so you get 100 detections. So you have only one target. So you do the gating. How many measurements do you expect to fall inside the gate? It can vary, right? It can be 100 too, but in real life, 1 or 2 or 3 maximum. Usually that's the case, right? So that means in the data association, by simple gating, you remove 97 of the measurement. Right? Now the problem comes to those 3 measurements. Which one is the correct one? Gate is eliminating impossible detection. Then we go into that and pick the best one. Is that clear? Okay, can somebody answer to that question? So I said that gating is done in the measurement space. He asked, why can't we do that in the state space? Is that right? Okay, so then your question was, okay, she agreed that we have to do in the measurement space. Then she asked why we use S, not P. Is that right? Right? Okay. Can somebody explain that? Because she agreed that we had to do the gating in the measurement space. Now her question is, why do we use SK instead of PK given K minus 1? Help me to answer this question. Anyone? Please think and answer. Right? This one intuitively you should be able to answer. Right? Think in terms of units. Think about units, okay? So what is PKK? That is in meters. Space. Yeah. So how can we use that in the measurement space? We cannot use. There's no meaning to use that in the state space. Anyone else to add anything on that? Is that clear? We can't use that, right? So basically it's a conversion, right? So convert it as this and do it. Okay? So that's why yesterday I was talking about that. P is in the state space. So you can't bring something in the state space to the measurement space. Okay? Okay. I believe this is clear now, right? So the idea of gating is to eliminate it. So now explain through graphically, I said that you row an ellipsoid, if it's outside, you say that's not the possible one. Now we are going to do that through math. Yes.
State space.
Innovation is, okay, there's a quick question on that. Innovation is on, yeah. I think I asked that yesterday too, right? What is innovation? Innovation is what? That minus that head. How can that be in the state space? Innovation is that minus that. So that is a measurement, that is a measurement. So it cannot be in the state space.
Same
No, when you are multiplying by h into x, now you are going to measurement space from the state space. H into x, then you are subtracting this, right?
So in the Kalman filter, like we have set up an equation. We don't split which is measurement space and state space. You may need to split. You do it.
Both are in the measurement space, state space, and the same Cartesian frame.
Which one?
Cartesian or polar position.
Which one? Both means which?
Measurement and state.
No. X always in the state space, that in the measurement space.
So then we are taking now we are getting r theta phi vector, r theta vector. For example, if I'm on the sensor, I'm taking x and y.
Yes, okay. So his question is this, right? So like the measurement is. So his question is that the state space is x and y, and the measurement space is also x and y. State space and the measurement space. Can I say both are in the state space? That's right. That's what you are saying, right?
Innovation is done x and y coordinates.
So, but yeah, to generalize then, I wouldn't confuse this like converted measurement and that. Even here, I would consider this as, yeah, you can do that. But even this, I would separate the state space and measurement space because state space include x dot, y dot. Measurement space is only x and y. If you think it mathematically, those are two different spaces, right? So anyway, even if it's like this, I would say this is state space, measurement space, innovation is done here. Okay, so always the innovation or gating is done in the state space, measurement space.
If you are trying to gate Z, that is the measurement. So you have the covariance of Z hat, that is the predicted measurement. Why are we taking Z minus Z hat covariance? That would be smaller. But what is the intuition in choosing the Z minus Z hat covariance?
Okay, yeah.
So what we are thinking is innovation will be in my state and not in the measurement. That's what.
Okay, let us go this way, okay? This is R and theta. Okay, so you get a measurement here. Okay, and the measurement has a covariance like this. Okay, and this is that. Okay, now you have that head somewhere. Okay, is that clear? So this is your predicted measurement location from the calculator. This is the actual measurement that you get, and this is the R. Okay, now what do you say? Is it like coming from the same target or different target? By looking at this, you think that these are not the same, different target. So, but that is not right. Why that is not right? So, this is a sat hat, right? So, what is the covariance of that hat? So, that hat also has a covariance. What is that? Say that is say like this. Can they be from the same target or not?
The Z-hat is predicted state.
Predicted measurement. So now if it is like that, you see that this can be from the same one. Okay, now let's go back to the sound of the equation and see what we do here. Okay, now here, okay. So first I plotted this one and this. Is that right? That's what I had like this. Okay. Then I had this one that is somewhere here. Okay. So now I am saying this part, not this, only this part. Take only this part. This is a covariance of this. Correct? Even though I predict that has some uncertainty due to my location error. So that has something like this. Right? You want to factor both of them to decide whether they are from the same or not. That is what we find the difference between those two and use this covariance. That is equivalent. That means checking whether those two ellipsoids are intersecting is same as finding this innovation and see whether that is falling inside the code.
If the innovation that's taking that those two ellipses are intersecting.
Yeah, so you can think of it. We have to. Okay. So definitely we have to use this covariance in that association gating part. So right? Okay, now if we go back to this, I think you have to clear your doubt somehow. The innovation is always in the measurement space, not in the state space. Okay? Yeah, yeah. Okay. Okay, now I was explaining through graphically. We are not going through that graphically, right? That's not coming, right? So what we do is this is the equation that we do. Look at this. So what we do is we find the normalized innovation. So you find the innovation and multiply by the S inverse and that you get some values, say for example 8.2 and this is the 9 as the gate size. If it is less than that, we say that it's inside the ellipsoid. Right? That's graphically the same as that. You find that normalized innovation square and it's less than the gate size, we say that just that measurement inside the gate. Clear? Instead of drawing the ellipse, basically you do this. You find that is given to, that is the measurement that's given. This is the predicted measurement, and this is the S. Then you calculate the whole thing, compare with the 9. If it is less than 9, that. Clear? So that's the gating. Okay, that's the gating part. So this is an optional gating. Post gating is an optional gating, but I do that in my tracker. Always I do that in my tracker. Okay, let me explain what is post gating and the purpose of it. So far what I did is the filter gating, but I want to do post gating. The reason is to reduce the computation time. Only reason is to reduce the computation time. So whether you use a coarse gating or filter gating, the results, final result should be the same. Okay. So main reason the filter gating is the problem with this. For each measurement we have to find the S inverse. And also you know that every measurement can have different R because of the converted measurement. So for every measurement you have to find the S and you find the inverse and do this. Because of that, because of this, if you have 100 detection, so you have to find 100 S inverse as calculation inverse. Okay, let's say it takes 10 seconds to do this association. Filter gating takes 10 seconds to do that. It will take for years, especially if you use IMF, then it becomes even more, right? So it looks simpler, but in the trackers, most of the time is spent on the data association. So that way, so if you have 100 detection, it takes a lot of time to do this association part. Idea of filter gating is to reduce this S inverse calculation. So what we do is, so we are going to do that in the state space of X and Y with a converted measurement. All the converted, so this is your state, this P. You have all the converted measurements here and here, right? So what you can say is, these are like not possible. Only these are possible, right? So idea is to avoid this S inverse part. What we do is simply this. You have your X hat, you know the B max, and you know the capital T. So you draw a big circle around that. Say that radius is, say, for example, 300 meters. But your whole coverage could be 100 kilometers. Right? So in the 100 times 100 kilometer range, 300 meters is nothing. So if you have 100 detection, if you put simple circuit, no inverse, no calculation, just simply putting a larger value, like say that this is exact, the converted measurement is outside the circle, I'm not going to consider that. That's like a coarse gating. I can simply reject. Obviously, you can say that, right? So this cannot be the case. So that is the idea of coarse gating. So out of 100, by using coarse gating, maybe most of the time you can eliminate at least 90 or 95. Simply you remove 95 of them, checking the distance with this. Then you have to find S inverse only for these 5 detections. Then the combination time maybe becomes like 0.8 seconds instead of 10 seconds. But the final outcome, final data association should be the same, no difference. Okay? So I repeat that the idea of coarse gating is to minimize the computation time. The result should be the same. So avoid calculating the S inverse for each measurement. In the normal calculator, you would think that we calculate S inverse only once and use that value for 100 detection. But that is not the case in general case for radar. So we convert a measurement. Each measurement has different R. When the R changes, S changes. Right? So then every measurement you have to calculate different S value. Right? And also in addition to that, in some cases, even the time is different. Each measurement has a different time. Then even the prediction is different. Do you understand that part? So in order to find S, because if you go deeper and deeper, there are so many problems. So what you do need to know is you have to find xk, even k plus minus 1, then you find S. You can think that, okay, I do that only once, and you do this 100 times, because R is different. That is one case. In another case, if it is a rotating radar, measurement 1 has time 10.0, the measurement 2 has time 10.1. It's a rotating radar. Every measurement has different time. Then what do you need to do? Even this one you have to do 100 times. No, like so your radar is a phased array, so everything comes in one time. I'm not talking about phased radar, say rotating radar. So that means so you get only one detection at 10, end of the detection at 10.1, the rotation time is 2 seconds. Yeah, go ahead.
Each point.
Yes.
Then also we get multiplication.
Yeah.
Then one target, 100 minutes other target.
So even like so, if as long as multiple target forms in the same beam, so you may have say 2 at also 0, maybe M3 at t equal 10.1. M4 is same time 10.1 and so on. Right? It can happen. But what I'm saying that so even this has to be done 100 times. For each measurement you predict the state, then find S and Q. So because of that, overall it's a computation is high. Okay, keep that in mind. Okay, that is the idea to avoid using the filter gating, the force gating, eliminate obvious unnecessary detection, then use a filter gating to narrow down and pick one. You understand that? Okay, good. Now we are going to, from now onwards, we are going to talk about those 5 detections. Okay, so now we started with 100 detection. So we do the filter gating. We have only 5 detection. We want to decide which one is correct from that. Okay. So let's consider R and theta. This is your x hat. Sorry, not x hat. Hat. And you have 2 measurements. One measurement over here. Measurement here. We are going to use nearest neighbor. Okay. So that is the approach for data association. You have your predicted measurement here. Okay. And you have 2 measurements here and there. You want to pick the right measurement using the measurement that's closer, nearest, closest to the predicted location. Right? So in which case, which one is the closest one? M2. Any other answer? Could you raise your hand if you think the answer is M2? You have to raise the hand for one of the option, okay? M1? None of them? I don't know. Okay, but in this one, what do you see?
Visually.
Yeah. Pardon? M1? M2. Okay, M2. So I'm saying that M2 is not the answer. Then why do you think that is not the answer? Because nearest neighbor is not simply finding the nearest one here. Okay? So that because I just want to explain the nearest does not mean in this one you say M2 is the nearest. That is not the nearest. Okay? Okay, now let me explain that. say this one, so this distance is 10 meters and 0 degree. Okay, that's the distance. This one, the distance is 0 meter, 0.3 degree. Are you okay with that? Which one is closer? Pardon? M2 is closer. Okay, why M2 is closer? Hmm? Okay, now let me see. Let me explain. Okay, 10 meter. 10 meter, 4.3 degree. Which one is smaller? Which one is smaller? 10 meter or 3 degree? Which one is smaller? You can't compare, right? You can't compare apple and orange. Same issue here. So they are in different units. You can't simply compare that. Right? You can't say that this is nearer than that. Because one is in degree, the other one is meter. How do you say that which one is closer? Okay, that is one reason. Okay. The other reason is that.
Other is 0 meters away. Because
Pardon?
like M1 and M2, both measurements are having the range and R and theta.
Yes, but in this case, one case the distance 0 meter, in the other case 10 meter, 0 degree, in the other case 0.3 degree. Right? So that means, so you are comparing this versus that, right? Because others are 0, right? So you can't compare, right? Okay, now let's consider, okay, therefore I want to simplify this problem. So that, so you have x and y. Okay, I simplify this, x and y. Now there's no unit issue. Now I have this, I have this, and I have this. Now there's no unit issue. And now I agree with you that this is close to that. Is that okay? But still, with the nearest neighbor, we may get this as the associated measurement. Okay? So by nearest, this could be the nearest, but the association can go with that. The reason is that US, say US is something like that. Which one is nearest now? So I like this is an extreme case. I say that I can't consider that, it's eliminated. So I don't want to eliminate completely. I draw like this. So which one is closer? Right? So the closer in terms of the prayer as well. Right? So now this is closer compared to this. This is almost close to the edge of the probability, but this is closer to my prayer equation. Okay, so that is how we define the nearest graphically. So now we go to the math part because like sometimes you can follow the math, but you don't understand how it would. Right? This is the reason the nearest neighbor is defined as. So you find this. This is same as what we used in the gating as well. Right? The same one. The same one that you use in the gating, you are going to use the same one here as well. So the distance is not the actual distance. The distance nearest neighbor and this is the distance. You want to find a measurement that minimizes that. So that is a normalized distance. So the innovation time is inverse. That is why I say because of inverse, it's inverse. The measurement here might be closer than measurement over here. Yeah, if it S is identity, then there's no weight in the x and y direction. Then this one becomes close, right? So that basically you are saying if it is circle, identity is a circle, right? Circle means the prayer is equivalent, then you could pick the closest one. Okay, so that is intuitively, but if you just want to follow the math and implement something, you calculate that distance. you calculate the distance and pick it. Okay. So even though this one is single target, as long as they are not overlapped, there's no overlap, even the multiple targets can be considered as the single target, two single targets. Okay, that's how we define single target. As long as these gates doesn't overlap, we consider two single target. Then if we have few measurements here, this one we don't care anywhere. These three measurements, I find the D1, I find the D2, I find D3, and find the minimum measurement that gives the minimum distance, and distance is defined by this. Are you okay with that? Any question on that? Because this is a basic and this is an important part. Once you understand that, you have a tracker to work. So most 99%, 98% it works. I have a tracker that has fancy MFA, MST, and so on. But 90% of the time I go with this type kind of tracker. So easy and works better. Right?
Perfectly.
Even if you want to use others, this is a basic. You need to know that, right? So nearest neighbor you have to know, right? And not much to understand. That's all. That's all you understand. Like you find a normalized distance, you pick the minimum. You do the gating. So with the prompt, you find the gating. Okay, I have only 3 of them. Then find the minimum. When you use a gating, already you have calculated it. Pick all of them and find the minimum. Yeah, right. So then you repeat for the other target. Multi-target, that this actual multi-target is being done. So this case is not good enough. But multiple target, we are separate. That's the most cases. Like if you're tracking chips and others, most of the time they are not overlap. Once in a while they might overlap. But if you write a papers and multi-target, or even if you want to extend the angle only tracking for multi-target, then you have to handle that. Then we don't consider as a multi-target tracking problem. You just have to separate one, then it's not a really challenging problem for us, right? So multi-target means having overlapping. Okay, that's a little complicated. But if they are not overlapping, so like you do that seek operation twice and do that. Okay. But in this case, if you have detection here, or let me do this. Okay, so you have 3 detection. So we can't do that one by one. We have to do that globally. Right? So one, if this one goes here, then this should be the answer. Because that measurement cannot be shared with this and that. That's the main problem. You can't share the same measurement with same track with just 2 targets. So if this goes with this goes that way. Or you go this way, then this goes this way. Then if you find the total distance, say this is D1 and D2, and say this is D1 bar and D2 bar. Then you find D1 bar plus D2 bar and D1 plus D2 and find which one is smaller, then you go with that. But you have to jointly consider both of them. Okay, that is the problem with multi-target tracking data association. Okay, so this is how you do properly. This is called global nearest neighbor. Okay, this is called global nearest neighbor. But in the assignment that I assigned, so we don't do that. Even in this one, you can take a shortcut. Okay, so that it works a little bit. That's not optimal. What you can do is you go with this. You take the first target. Okay, so these 2 are in the gate. You find the closest one, so you associate that. Then when you go here, you remove this option. Then only consider about this, you go here. But it may not be the optimal solution. May not be the optimal solution, but it's a feasible solution. One solution that can work. But optimal solution may be going this, and this might be the optimal solution. But since you pick this as the first target and you don't care about the other target, this is the nearest closest. You take it and remove from the possibility for the next target, then you can associate with this. That's a simple approach to approximation. Is that clear? Okay. So anyway, so this is how the nearest switching work. As long as I believe at least you understand this part, if you do that, this is a small change that you would do to handle the basically like if you want to do suboptimally, do one by one. First take the first target, do the gaining, associate and remove that from the measurements to follow, process for the following targets and do repeat. That's a suboptimal approach, but it's reasonably okay. Okay, once we do the data association, the tracking problem become a filtering problem. So clear? Once you do the data association, what do you have? You have a track and an associated measurement is there. Then you use the common filter. Right? So then it's the simple filtering problem. Okay, that's what it says. But I talked about only this, okay? Nearest neighbor or global nearest neighbor. But in the papers and so on, there are several other algorithms handle that. PDA, MST, MFA, and so on, right? If you want somebody want an optimal tracker, I would say you implement an MST. I'm not going to talk about that because that itself is a huge one. There are even book on MST itself, right? So MST is a multi-hardware tracker. So if you want, you can implement that too. Okay. MFA is a suboptimal, like not MFA is an implementation of MST. You can't say MFA is a different tracker. MFA is an optimal implementation of MST. That is another tracker. PDA is a slightly different tracker. So I would say if you want to start with the data, I would say implement nearest neighbor, see how it goes. Then think about adding additional options to your track. Okay. Okay, so we talked about initialization, data association. The last big part is the track management. This is compared to others, track management is simpler, but it's crucial. So algorithm wise simpler, but tuning parameters quite little hard. Okay. Okay, track management. What we mean by track management, right? So, like in the last class, I just mentioned about that. Usually, we have three stages: tentative, confirmed, then. Say the track can have only three status: tentative, confirm, and then. Whenever we initialize a track, we always start from tentative. Then the next time step, it can be tentative, or it can go to the confirm, or it can be dead. Are you okay with that? That's one way of going from tentative to the confirm. Once it's confirmed, we don't allow this. Okay? We don't allow that. So you can't go back to the tentative. Once you confirm, you don't go allow. At least this is my rule, I would say, right? So if you want, you can come with your own rule. There's nobody would stop that, but I don't do that. Okay. Then it can stay in the confirm. Then it can go dead. But if it's dead, then it is dead. You can't go back. So we don't allow. I don't. Maybe we don't. I don't allow that. Okay. Those are not allowed. Now the track management is deciding when to do that and when to do that. Okay, so the question is when to do this, when and where. So this is called promotion. So you are going promoted as a confirm. These are termination. When to go from one state to the other. That is the basic questions that we answer in the track management. Okay. So for example, one of the possible sequence of states could be, ideally could be tentative, confirm. And then this could be one of them, right? So if this is the case, this is a termination latency, confirmation latency, maybe this could be the termination latency. Understand that? Right? So, but this could be the sequence of the state of a track. Clear? So we have considered three types. Tentative, confirm, dead. Promoting tentative to confirm, deleting and deleting. So we are going to talk about two different approaches. One is the quality based and the logic based. Okay, in the slide, I think I have quality based first, but I will go to the logic based and come back to the quality based. Okay, logic based is easier too, but I will start with the logic based. Logic based, only this slide, nothing else. Okay, one slide explain everything. This says now it says that you remember that we talk about association history, right? So we have a track. Say whether measurement is associated or not. When you create a measurement, it's associated. Say this is associated, not associated. Okay, first of all, you have to understand this part. Okay, for a track, we are initializing at this time. One indicate that this time step we have associated measurements to track. This means the next time we have an association. This means we don't have any measurement inside the gate or we don't associate anything. We don't associate it. We association, no association, and so on. Is that clear? The logic based on this. So initially, I have tentative here. The status is tentative. Next, I want to decide is tentative or not. The logic base says, or we say that m out of n. Now it says that, say, if I have 3 out of 5, I will confirm. So this is the logic I use for confirmation. In last 5 frames, if I get 3 detection, I will promote. Otherwise, I will terminate. Correct? So after 5 frames, okay. If I get 3 detection, in this case 3 detection, so I will confirm. Are you okay with that? So now, for an example, if I have like this, what do we do? This. Okay. So in this case, it becomes T, and confirm. This is T. Clear? Then after this, it won't have any value because it can't continue after that. That's simple as that. So you define this 3 and 5, it comes like that. Okay. Similarly, like this is for confirmation. For terminate, pardon?
It's the upcoming 5.
Okay, wait. I will explain. This is for tentative. Okay. For tentative track, I have this logic. Okay. For confirm track, I have a different logic. Okay. So the confirm track, I have a different logic. If I get at least one measurement in 5 frames, I will maintain. Otherwise, I will terminate. Okay. So that's what happens. Say if you have it, for an example, in this 5 frame, so I have more than one detection, that's fine. So in this 5 frame, more than that's fine. Here, even that is fine. But if you have one more zero, then it becomes C, 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 E, D. Is that clear? So this is the logic I see. 1 out of 5. In last 5 frame, at least one detection, I maintain. This could be 2 as well. You can decide that. As long as this many detections are there in the last 5 frames, I will delete it, maintain, otherwise delete. Is that clear? Okay. So that is the tentative track. We have different MN values. Confirmation, I have different MN values. We do it. Okay. So that's all about the logic-based track management. Now let's talk a little advanced on this. What is the maximum? You understand this part, right? Okay. Now let's say for the tentative track, the logic is 3 out of 5. Okay, I use 3 out of 5. And the measurement sequence is 1, 1, 1, 1, 1, 1, 1, and so on. What is a confirmation latency? One answer is 5, but you said 3. Okay, any other answer? If you implement in a lazy way, always 5. Not always, in this case it's 5. But the optimal way of implementation is 3. Okay, so you have to implement in optimal way that such that there's a 3. Because you know that if it's 3, after the unit we get 0, 0, we are going to confirm. Why do you wait? Right? So that way, so you would confirm here. So that is a like small change in your code. You can't write a paper out of it, but when you write the code, you have to make sure that you do that. Right? For an example, let's consider this. 1, 1, so tentative and tentative. 0, what is that? Next. So I'm using 3 out of 5.
You write the next.
Tentative. Okay, tentative. 1. Confirm. Not tentative because you have enough 3, right? So 10, confirm here. Right? So now I say 1, 0, tentative and tentative 0. What is that? Tentative 0. There. Okay, so you small change in your code such a way that you don't want to wait too long to delete it, you can delete that. Okay? Okay. Now, I think I set a question on the quiz as well. Let's see. So now this is what I was saying that, right? So when they play the real data, the harder part is what should be this number and what should be that number. And what is the effect of it? When you use 3 out of 5. So there are several cases you have to consider that. Let's say you want to use 3 out of 5 versus 8 out of 10. Okay, let's consider 2 cases. One is 3 out of 5, other one is 8 out of 10. When would you use this? Or let's say you use both of them. Which one has more latency? This has more latency. Which has less false alarm? 8 out of 10 has less false alarm. That's the benefit of that. Right? Now let's say you have 3 out of 5 and 4 out of 5. Okay, how do you do that? Which one has less latency? This is better in terms of latency. Number of false alarm, 4 out of 5 is better in terms of number of false alarm. right? So you decide based on, mostly you decide based on the sensor P. Tensor P and lambda. There's no like direct math equation that map into this number, but usually these are the two things that you have to factor when you pick the value. Okay, so if you change from one to the other, what happened to that when you have? Okay, now let's go to the other one, the termination part. Okay, let's think about termination latency. Termination logic, say I use 1 out of 5 versus 2 out of 5. Okay, which one is better? Termination latency is 1 out of 5, other one is 2 out of 5. Pardon? So let's think about termination latency. Which one is better? 1 out of 5 will have a better latency or versus 2 out of 5. So like 1 out of 5 means I say that if I get at least one detection in 5 frame, I will terminate. That means what's the minimum latency that we can have? 5. Right? You need to have 5 zeros before you terminate. In this one it says if you need to have at least 2 detection in the last 5 frame to maintain. So what is the latency that you can have? Even after 4 zeros, you can delete it, right? So that means this will have overall less latency. Is that right? Okay, can I say that with this one, always latency, termination latency is less than 5 or equal to 5. Can I say that? Do you understand my question? For termination, I use 1 out of 5. If I use this logic, can I say the termination latency is always less than equal to 5?
Termination date both are same.
Yeah, termination and data are the same. Can we say that? You can't. Okay, you can't say that. Okay, so let's say this. Okay, actual target stops here. Okay, actual target stops here, and the track goes like this. So this is 1 1 1 1 1 1 1 1 1 1 0 0 0 1 0 0 0 0. What is the reason to have this one? Why do we have this one here? Anyone? It could be a false alarm that associated with the target. Then what happened? Then it goes longer. So the latency can be more than 5. Okay, so we are not saying that. It's always less than 5, but it can be more than 5, but it cannot be less than 5. That's what I was saying, right? But in this case, this is better in terms of less termination latency. Are you okay with that? Right? No? So I am saying that, so if we have 1 1 1 1 0 0 0, this is confirm, 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 confirm. If I use this and if I 0, what is the next one? Dead to confirm. Dead. So at least if you have 2, so I won't have 2, so dead. But if I use 1 out of 1, it's going to be C. Then another C, you wait D. So that way little longer, longer latency with this. You see that, right? So that is better. Then what is the drawback of this? Oh, there's always a drawback. You can't say that this is better than that. So what is the drawback of this compared to this? So what is the benefit of this?
False alarm will be easy.
Identification of false alarm. Okay, think more. Okay, now think about the performance metrics that we use. That's why I started with performance evaluation, right? Think about the performance evaluation. and see which one will be affected by this. Yes, that's the main thing. So you may break the target. So that means, upon example, in the middle for some reason, I got some zeros. Something like that. Or another zero here. In this case, this can maintain this track, but this will kill the track at this point. Right? So that way, it will break the tracks at this time. So if you try to reduce the confirmation latency, you may introduce a break. But if you ask me which one is better, 1 out of 5 or 2 out of 5, I can't tell the answer. You have to run with your tracker, the data, not the tracker data. So data and see how it works and what you want. That depends on the user. Some users prefer to have a break, but they don't want to have a larger latency. Some other latent users may not want the latency, but breaks, but latency is fine. So depend on the user you pick, because that different user means the customers they want, right? So that like if you are a leadership person, you are the customer, right? If you are the research people, you tell what you want, then we pick a value based on that. Clear? Okay, that's all about the logic base, nothing else, right? And that is why easier because just numbers and understanding is easy, but finding the optimal value for this is not an easy problem. Okay. Okay, so that is about the logic base. This one, if you want, you can avoid this. But usually I use this to reduce lots of tentative tracks. When you implement tracks, sometimes you get lots of tentative tracks. So what we do is, we always want to go this way. That's a little complicated. If it's complicated, don't worry too much about that. But always you do that. Instead of saying 3 out of 5, I convert to this. First 2 always has to be there. After that, I would say even if you have 1 out of 3, that's fine. So that means it's a little trickier. First 2 has to be there. Do you think this is equivalent to 3 out of 5? Are they equivalent or not? I say that first you need to have 2 out of 2 satisfied, then 1 out of 3, then only we confirm. In the other one, I say 3 out of 5, then confirm. Are they equivalent or different? They are different. Which one is more stricter rule? First one is stricter, right? So that means, for example, 1011 is valid in this one, not in that. So that way, so you can eliminate a lot of unnecessary tentative tracks by this. So always have a 2 out of 2 that say I remove a lot of false alarm, but I don't want to confirm. Just wait a little bit and then correct. Okay. So that's all about the logic base. Then I will talk. Let's talk about the quality base. I will finish by 1 o'clock anyway. So I have a lot of slides, but at least we'll stop with the track management for now. Okay, next is the quality base. Quality base is also not that hard. Idea is this. So this is a time A and the quality. Quality of your track. Quality is always 0 to 1. Okay. So initially always we start with 0.2 for example. Then if you have an association, then the quality goes up. Then it can be like this. Then it can be like this, something like that. Okay. The quality fluctuates. So now whenever association quality goes up, whenever you don't have association, it goes down and so on. In order to do the track management, what we do is we have some thresholds here and 3 threshold levels. We have 3 levels. Okay, let's say this is 0.9, this is 0.05, say this is 0.005. Say 3 levels, right? This is the initial value I give the quality. This is 0.9, this is 0.05, and 0.005. Then let's say we have some equation to update the quality. We'll talk about that, how to do that. But now assume you have an equation to update the quality. So what we do is, after this point, tentative, 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 confirm, 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 confirmed, 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 confirmed. You understand that part? So once it's confirmed, we wait until it goes below this threshold to delete. Okay? But if another track, if it goes like this, then I say T, 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 and then. Okay? So I have two different levels. This is usually higher than this. If it's tentative and it goes below this, I will stop that, terminate at this point. But if it's confirmed, then I will wait until it goes below this and make it there. Is that clear? That's all. That's about the quality. Now we have to talk about how to update this graph to find the quality. But the simple as is, you define three levels, 0.9, usually that's enough. I think that's a normal, reasonable number. 0.9, 0.05, 0.005, three levels. Promotion, have to reach 0.9. Termination, if it is confirmed, it has to reach 0.005. Below that, if it is never confirmed, as long as it goes below 0.05, I terminate. Is that clear? Okay, if you understand this, that's the main thing. Now you want to see how to update the quality. Okay. So that equation, what we do is, we start with the point 2. First, we predict the quality. With a survival probability, usually we put 0.9, something like that. What is the probability that the target will survive? Your prayer, right? So if the target is there in the last frame, what is the probability to have the target in the next frame? So usually we don't put 1, so 0.9 or 0.95. This is like a predicted quality, similar to Kalman filters. Instead of predicted state, this is the predicted quality of that track. Okay? Then, this is the update equation. So if you have an association, then use this. No association, you use it. Okay? So you don't worry about the derivation. Now, if you want to use that, what are the things that you need to know? PD, this is a likelihood of getting the measurement, and this is the false alarm rate. Okay, and in this one, same thing PD and PD as well. So use just follow the equation. Okay, don't worry about it. Okay. So it depends on how close likelihood. Basically, in addition to 1 and 0, so if you have a detection here versus here, we'll have a different quality. Okay, so if the measurement is closer to this, the likelihood is high. So the quality, so this is, if it is a PQ is a 0.6, if you associate M1 and M2, maybe if you associate with M1, then maybe quality might goes to 0.89. If it is M2, then the quality could be 0.93. It depend on the how close to your target also affect the quality. That is why people prefer the quality based over the logic based. But I personally use logic based. But I know I don't be biased. So this is one place I can't comment too much about it. Quality work better, I would say, as long as you know the PD and EFA values. But in real world, you may not know these values accurately. Then the quality base has some issues, so challenges like that. So that is why usually I don't use quality base. But there are people who prefer quality based. I don't have any preference on that, so you can decide to implement both of them and see which one works better for you. Okay. Lambda, I didn't bring equation, but any data association you have lambda. Lambda is the in the scalar dimension. If you have a Gaussian distribution, so this is your sat hat, and this is a z. This is a z. Then this is a lambda. The likelihood of getting that measurement, right? So that is the sorry, this is S, that is S, and then what's the likelihood of getting that measurement? This thing, one dimension, but in the two dimension or whatever it is, you just use a Gaussian distribution, substitute this and that and that, and then get the line. Okay, so then finally, and this is the last slide on this one summarizes what I was telling. If you have 2 out of 3, then if the PD, sensor PD, okay, the sensor PD when it is lower, then you see that confirmation latency increases. That's obvious, right? If you have a more chance to miss a target, then the latency increases. Is that clear? But if you go from 2 out of 3 to 1 out of 2, this is reduced. That's better. Right? So when you go from 2 out of 3 to 1 out of 2, the latency is reduced. That's better. Now, if you go here, when you use 2 out of 3 for a given false alarm rate, you have this. But when you go from here to here, this is increased. That's bad. Right? So you see that when you go from here to here, we get more false alarm compared to the other case. So when you go from here to here, we have a less latency, but we have more false alarm. That's how they interconnected. Right? So that's how, say, if you want to pick a value, say you do your simulation, then come up with this table, and even in this table, I don't know how you will pick it. You have to pick it. You have to pick one value. At least you know that, okay, if I pick this is what I get, I'm okay with that, then you decide. Okay? Okay, finally, the comparison is quality base is easier, and also it works with non-uniform clutter time. That is the other thing, okay? So usually I don't handle in my tracker. That is a main problem. Usually you may need to handle. Let's consider a case in which R and theta, and so you have a lot of false alarm in this region and less false alarm here. Okay, that is called heterogeneous clutter. Heterogeneous clutter. Homogeneous clutter means clutter is everywhere as uniform. But heterogeneous means you have high clutter region here and less high clutter region over here. Okay, so intuitively you want to have a different amount of n value for this versus this. Are you okay with that? But that is hard. Usually that's hard to define that. You can implement, but you need a lot of effort to do that. First, you have to define that region. Then the target can go from here to there. How would you handle that? That's the challenge. Well, you have to somehow do that if you want to do the logic base. This is harder problem. Quality base, you don't need to do anything as long as you know the PD and lambda here and PD and lambda here. So then for each measurement you associate that. Then for that particular measurement, use this PD or that lambda, that's fine. But the main problem is that you need to know that PD lambda for each measurement accurately. If you know accurately, the quality base is better. Okay. But as I mentioned, the challenge is you need to know this part and PD as well. Logic based, I would say easy, but it's hard to tune that for different languages. Okay. So it's already 1 o'clock. I would stop. Okay. But slides I have, maybe I will talk about this maybe in the tomorrow, like the start of the class tomorrow, or in the tutorial time if we get time. Maybe, so this is a multi-sensor case, how to use multiple sensors. I will just simply talk about how to use multiple sensors. And the other one is about outer sequence measurement. So what is outer sequence? Mainly I will explain what is outer sequence measurement and what to do with that. Okay, those are the two things that I want to cover. Then I think our current plan is to talk about track-to-track fusion tomorrow. And then a little bit upon the resource management tomorrow. And then on Friday morning also we'll talk about a little bit of resource management. And then that's all for the right? Okay. But if you have any specific question, we can discuss. Like,
Yeah, so I like if you recommend any books to the audience.
books, okay.
Yeah.
Okay, that is the other challenge that in the tracking community, there's no good book. Okay. In 2011, Barcelona has a new version. That is one book that you can read. Definitely you can read that. But it's pretty expensive. But if you can download it somewhere, like if you can have a subscription somewhere. I don't think they have ebook on that. But if you can find it.
On their organized.
Yeah.
Like you and also they have the IT.
Pardon? That 2011 is one book, right? Only one book in 2011. So if you have an ebook, it might be cheaper. Otherwise, you have to buy the whole big book, that book, and read that. And the other one is even I am editing a book with Mahendra Malik, but that is about advanced algorithm, but that's not good for the people who are starting from basic. That is the Barcelona book, this one. Other one is I like Samuel Blackman books. I like his book. I think that was in 1995, the older one, before 2000, but with less math that you can follow the concept. I think I would recommend that. But recently there are books like only focus on certain application, not about the whole thing. Barcelona book is the good book for that.
Yes.
Otherwise,
Tracking and data fusion and
Pardon?
2011 it's tracking and data fusion a handbook.
Yes.
Even
But there are other books. I would say every book is a combination of paper. Even Barcelona book, Samuel Blackman book, I wouldn't say that there's a combination of books, but the Barcelona paper book is kind of combination of their papers, so old papers and so on. But other book chapters, edited books, and any books are like combination of papers. So if you can find if you have subscription to IEEE, then getting the books and reading those might be an option. Hey, I have the reference somewhere, right? No? This is the one, I believe, right? That's it. Even for the course I teach at McMaster, I use this as a reference book, but I don't think any of the students read that whole book. I think nowadays they go with the slides, but if you want to have good understanding, I would recommend to use this. And the other one is the 2001 estimation book, by Bartolom Kiruba and others. Yeah, that is also good book. That's a lot of math, for sure, that's a lot of math, but that is a great book to learn about the basics. Usually when we have comprehensive exam for the PhD students, we ask questions from that book, right? Because that has a lot of math and there are so many questions that you can work on and come up with the it won't give an intuitive idea, in my opinion, but it has a lot of battery equations, right? But that is good for IMM. Definitely IMM, EK, Almafilter, that's good. And even the other chapter 2 and 3 are also good on that. I think random finite set, there are some books as well. I think like if you have somebody working on random finite set, then but that's pretty math heavy. I think I would warn you that like there are books with Don Mahler, but he's a mathematician, okay? So that way, so if you are not a mathematician, it may not be easier to understand. Particle filter, there are books on that, I believe, right? But again, like even particle filter, like taking the tutorial, Sanjeev Alam's tutorial, it might be easier than reading a book. Or you can find some theses. Sometimes like you can get thesis, maybe that also could be written somewhere. Some at McMaster, these are free. I think everybody can download from outside. Similar to that, several university releases their theses. So if you can get those as well, sometimes students explain well the basic part as well, right? And these days, the MATLAB has at least some built-in trackers and so on, then you can make use of that. Not for real system, at least to see how close your algorithm with them, right?